on the equation.
All right, here we go. Let's talk about matrices. Are you ready? No. So, like I said, my assumption is that your prior experience with matrices is nada, right? Nothing, no. Okay. So let's start by saying what a matrix is. And again, some of this will feel procedural today because you're like, what is this good for? And so some of today will have to be taken on faith. You'll have fun like pushing symbols around. It'll be fun. You'll see. But you'll still have maybe a question after today, like why? Why are we doing this? So stay tuned for all three of these days together. You'll see how they come together. And maybe you'll start to even see that today. I don't know. So a matrix is just a rectangular array of numbers. By the way, this hopefully, are you good on this sheet here? Right, this is like word for word. I just copied and pasted on here. So feel free to, as you're taking quote unquote notes today, you may want like a highlighter and or something like that, or you want to, or like annotate. Like if there's anything interesting that we say, or you want to write down. But I was like, I don't know. There's so many new words and symbols and notation that I didn't want to have to make you like write this all down. Okay, especially for things that are not like rocket science. This is a matrix. All right, there it is. It's a big rectangular array of numbers. I do want to like hone in on a couple little tiny pieces of notation though. I think you'll notice that we always report, this is not like optional, we always report a matrix as rows, number of rows by number of columns. And when we report its size or its order, sometimes we call it the order of the matrix. Okay, so if it has 4 rows, 3 columns, we call it a 4 by 3 matrix. And also the way that we double subscript each element of the matrix is kind of worth noting as well, right? So we always like A21 is the element in the second row, first column. So you see how we have this continuing preference for row followed by column. Okay, so let's get that out of the way. That is just a convention, but it's a convention that you all need to agree to. All right, each element, or sometimes they're called entry, is written in this form. If it's a square matrix, then we call it a square matrix. Rocket science. All right. And 2 matrices are considered equal if each corresponding element is equal. Column matrices and row matrices, that is a matrix with only 1 column or a matrix with only 1 row, can also be thought of as vectors, and you'll see why that's a powerful move soon. Rushing through this because you have this on your paper. If I didn't tell you how to add matrices together or subtract them, I think you would still do it correctly, right? It's element for element, the corresponding elements get added or subtracted. If I didn't tell you how to do scalar multiplication, that is to take a matrix and multiply the whole matrix by 5, I think you would still do it right. You would be like, do I multiply them all by 5, every element? And that would be right. That's exactly right. So there's not a lot to say about that, so let's just try it. Are you ready? If you haven't already started. Try these problems at the bottom. I'll call some people up in a minute or two to do these. I have not checked these answers. Please check their work as they come up here.
Oh no, yeah, if they have.
What do you think?
I want to see if I can do that.
Are you going to be able to take that, Daisy? Take it. Come. Are these all right, A, B, and C? Ivy, what's the answer to D?
No, I'm doing D.
Wait, you're just going to steal it like that? Did I call you up here? I don't think I did. No, it's all right. You're forgiven. Can't do it. Yeah. Why can't you do it? Cheyenne? Why can't you do it? Yeah, go back and look carefully at the definition of addition. It says if matrix A and B are of the same order, then we can define A plus B, right? So there's a very small word that we kind of skimmed over, but it is true that if you just generally like pick randomly two matrices, odds are that like you can't add them. Like you just pick like you'd have to be very lucky. They'd have to be the same dimensions. And and then part E is interesting, yeah? Tried to trick you up there, but looks like you figured it out. Oh no. Devastating. Wonderful. I like all the work you showed.
Oh, look how much work I shared.
All right. So is that cool for the last one as far as the kind of reasoning that you might be using to get to these answers? I mean, there's only so much I can do to try to trick you up when it comes to just like addition, subtraction, scalar multiplication with matrices. I tried to make it tricky, but somehow you conquered it. Okay. Good job. Good job. You want to multiply matrices? This is where your mind gets blown a little bit. Are you ready? It doesn't. The reason we're going to give great pause here is because it doesn't happen in the way you probably predict. It's not element for element. Okay.
Oh yeah.
All right. So this is on your paper, but let me just take a moment to unpack this like real heavy notation coming at you. Are you ready?
No.
All right. So we define the matrix product. Let's call it this matrix C. Ij, right, where all the elements are indexed as Cij, where each element, I want to make sure you're clear on this, each element of the product matrix is formed by taking this calculation for each element of the matrix, okay? So if you're in, let's say we're doing trying to figure out what is in the product matrix, what's the third row, second column? That is, what's C32? So then what is this? This is A31, A32, A3, all the way down to the end, right? A3R. So what are all those A coefficients? Those are all, all those A elements. Those are all elements from what? From the same row, right? Namely the row of interest. What is B taking from? This is B1, say if we're doing like C32, like I said. This is B12, B22, and all the way down to BR2. So what are all those? Those are all taken from matrix B, and those are all from the same column. Aren't they all from column J? It's every element from column J. So the picture says that too. I just want to make sure you're clear, right? So how do we get this one element right here? We multiply every element of the row from A by all the elements of the column from B. Right? And add them. So this one times this one plus this one times this one gives you that. Here it's just two products to multiply and add. Does that make sense? So row by column. You take the row and you multiply by the column. We'll do it here with this example in a second here, and you'll get a feel for this. Row creates column. Now, I want to make sure you make a note of something here. What that means is that in order for this multiplication to even make sense, the number of elements in the row of A, that is the number of columns in A, has to match with the number of rows in B, doesn't it? In order for these to have the same number of things in these green boxes, the number of columns in A has to be the same as the number of rows in B, right? So if you're doing a 4 by 2, which is what this is, multiplied by a 2 by 3, let me say it again, the number of columns in A has to be the same as the number of rows in B, yes? And then once you do that, what's the size of your product? Note that this is weird because you get like you're multiplying matrices of different sizes under this definition. And you get a matrix of a third size, which is 4 by 3 matrix, right? And it should be clear why that comes out to be a 4 by 3 matrix, because it's going to have the same number of rows as A has, and the same number of columns as B has, right? It won't fully make sense until we do one together. So let's do this one nice and slow and careful. Okay, slowly and carefully. So we'll do AB here, which is in fact just exactly the picture we have there, right? We have a 4 by 2 times a 2 by 3. So I think that's going to work out. It's going to feel just like that picture, but let's actually work it out. I'll do the first row with you. Here we go. All right, so what did this call for? This element right here, the very first row, first column of the product matrix will be first row, first column. First row from A times the first column of B. So what is that? That's 6. It's 1 times 6. Plus 0 times 1. Do you see why it's important that this have the same number of things as this? Like if you think you can do the product and it's actually undefined, you'll see soon enough, once you start doing it, that like when you start doing this, these don't match. Like that's got to have 2 things, and this circled thing has to have 2 things, or else it won't work. So 6 plus 0 times 1 is 0. So the first element in the first row is 6. Okay? Now how do we get the second element of the first row of our product matrix? That is this guy right here. We'll do it in green. It's pictured actually. This guy is pictured right here. It'll be row, again, what row are we in? We're still in the first row. So we use rows, first row, but this time second column, right? To get the first row, second column in this matrix. So that gives you nice here. We get 0 plus 0. All right, I like that one. That was good. All right, and then last here. How do we get the last element in the first row? Yeah, still the first row, but times the third column, right? So that gives us -3 plus 0. Sorry, these are not very interesting in that first row, but is that cool? Can you do the next 3 rows yourself? Take each row, just the same way we did it, take each row and multiply by all 3 columns, right? So stay with the row and multiply by all the columns. Stay with the next row, multiply by all 3 columns. And check with your neighbor when you're done.
So you guys get take 0, -3, -3, -2, -4, -10, No. No, I did it. I did it. No, I said that I got a 30 as a matter of fact. No, I did it. No, I did. Oh, okay, I did say that, but I tried not to stay with
the first element in the row times the first element of the column. Plus the second element of the row times the second element of the column. So -3 it would be 1 times -3 plus 0 times -1. Does that make sense? All right, check me on these here too. What is it? -6 and 3 is -3. 0, 6. Is this -6? Check me on these here. Is that negative? Oops, 22. Is that right? 24 minus 2. Check me on these. 12. -10. Is that what you got? Somebody check your coming there. Which one?
The third column, second row should be 0. Third column, second row. The -6.
Like the -3, 6, -6. It should be -3, 6, 0. Yeah. The second row, the last line.
Second row, last column is -3 plus. Oh, it's 3 plus 3 is 0. Yeah.
Look, this is the best view you'll ever see. Look. Such difficult matrix.
All right, thank you for checking. That's why you check. All right, we good on these? Yes? Okay. Now you know how to multiply matrices. Let's make a couple notes about this process. Oh, wait, hold up. There was something else we were supposed to do. We're also supposed to do BA, right? But why is it true that we can't multiply a 2 by 3 by a 4 by 2? Right? Like we said, if you're not sure that you can't do that, just start trying it, and you'll start to see that if you try to do that, you'll be having columns in the first matrix. You'll have this matrix that you're starting with B that has 3 columns, and you'll be trying to multiply a row that has 3 entries in it then, right? By, in the second matrix, a column that has 4 elements in it. Problem, right? So even if you didn't know this rule and you started to do this as if it was possible, you'd right away recognize that this isn't going to work. The fact that these have 2 in them, 2, 2, and that happened all the time during your multiplication process was like, that's good, right? But if that doesn't happen, then it doesn't make sense, right? So, said another way, are these the same number? No. Okay. Right? 3 notes about matrix multiplication. Like we just said, BA, it's sometimes we don't even have a product. In fact, again, if you just like to pick 2 matrices out of the bin, it's probably true that you can't multiply them, right? It's kind of a lucky strike if you can. Again, you might be having questions like, okay, then why is it so useful? But I promise it is. One other thing to say is that when you can do it in both directions, like say you do a 2 by 2 and another 2 by 2, then certainly you can form the product AB, and you can also form the product BA, but in general, they do not commute. And this is not the first or the last time that you've seen an operation that does not commute, right? So that shouldn't, you might have questions about why that would be something true, but I think you'll learn soon why that makes really good sense for things we'll be talking about soon. Why, actually, we like the fact that it doesn't commute. That's a good thing, actually. And then if this doesn't feel familiar, let me just tell you that it should have, right? This idea of multiplication is one that we've thought about, this idea of multiplying stuff and then adding it is familiar. It's the dot product of these 2 row and column vectors, right? Right? Imagine someone just asked you to multiply these 2 matrices. Could you do it? Yeah, there's a 1 by 2 and a 2 by 1. You could do it, and the result would just be a 1 by 1 matrix. It would be not very interesting, but it would be just 14, right? It would be the dot product of those 2. I think for the interest of time, we'll skip. Well, maybe I'll pull this up here while you're working on these problems. But this is worth doing. It's fun. Like you can fill out your own 2 matrices and have it multiplied. It actually steps through and shows you piece by piece very slowly. It's cool. But I think you probably understand how to do it based on your success just now. All right. Again, on these problems, if you haven't start trying them right now. Some of these might be undefined. Be careful. I'll be on the lookout for that. So just I don't know. Have fun. Let's give it a try here. Let's do a couple of these. Yeah.
For the final example, this is a question not be
I don't know. I mean, where are your sticks?
Yeah, I did it wrong. I would be getting a recycler. Wait, okay, so it's 46 I had. Negative 63. No, wait, no, negative 54.
Yeah.
No, wait, no, it's negative 63.
Do you want to do that one?
Where are you?
Do you guys realize on C that by b squared we don't mean just square each element, right? We mean take b and multiply by b, right?
Yeah.
Okay.
Fun fact, that's the only
That is commutative. That's true. B times b is the same as b times b. Is it? That's a good question. I want you to think hard about that.
not if all the terms are 0.
Yeah, that works too, right?
Or if all 3 terms are 0.
Yeah, maybe you can make some broader points. I guess you could make an IAM.
That would be a very short IN. Very, very short.
Sophia, I did not get to this. See, are you slow? Because
Are any of these undefined?
yeah, D and E are
Both D and E can't be done? Alright, the D and E apparently can't be done according to Cameron. But what is she?
No, you can do E and you can
Both. All of them. I remember I read this line. I don't know.
It's m columns, then n rows.
I don't think you can do D or E.
E is a 2 by 1 by 1, right? But you have one side with 1 column, 2 rows, and the other side with 1 row.
Alright, hey guys, the bell's just about to ring here in a second, so hopefully you're having fun with this. One other thing, guys, that I did not emphasize today that I'll try to hit tomorrow is this extra piece here. Hey, can you move out of the way? Sorry, alright. Guys, so maybe tomorrow when we open class, we'll talk a little bit about how you can even use your calculator to verify these. There's nothing on the homework that requires that though, so you should be fine. If you want to noodle around with your calculator so you can figure out how to make it do matrices and do all the same stuff, that'd be cool. But we'll talk about that tomorrow. Is everyone doing the homework from the book? You know what's being asked? Okay. Homework from the book tonight. See ya later. It's exciting. I think A is okay. Is that what you got right? Yeah, a 2 by 2 times a 2 by 1 is okay. And you do get a 2 by 1. Row by column. No, the number of rows in this matrix is 2. It says 2 rows. I know. Have a great day, guys.